Yeah, in the last class we learnt about about dynamic logic. So today we'll try and understand what an domino logic is, which is similar to dynamic logic, but certain limitations of the dynamic has been overcome in this particular domino logic family. Okay, now we learnt about dynamic logic. It suffers from charge sharing phenomena, right? That means whatever charge is available here, suppose this is a NAND gate and now B is 0, it is pre-charged to, this is suppose this is being pre-charged to VDD initially. Now after that, now during the excuse me, during the evaluation phase, if B is 0, A is equal to 1, this is supposed to remain VDD, but then some charge from here comes through this A transistor and it gets accumulated in CX. So this won't remain VDD, but it will remain, it will go slightly lesser than VDD, and that is known as the charge sharing phenomena. So that is an issue with the dynamic circuits, and then there were two different conditions which we saw in the first case, where Cx is much lesser than Cy. So even a small charge which gets shared from Cy will result in large voltage increase across Cx. So we can assume in this particular case, since Cx is much lesser than Cy, this will reach the max possible voltage. And if you remember, what would be the max possible voltage out here? Because this is an NMOS, it cannot transmit a good one. So X can maximum go up to VDD minus VTN. Right. So in the initial case, when this was pre-charged, so the total charge available across the capacitor Cy will be VDD Cy. Now if you equate those charge, after the charge gets shared with some of the charge from Cy gets charged to Cy, so the condition would be Vy Cy. So Vy is the new voltage which is available now across the output node, and VDD minus VTN, because we are assuming that this is got charged up to the max permissible level, which is VDD minus VTN into Cx. Okay, so now if you just do some algebraic manipulation, and we can get delta V out, which is Vy minus the VDD initial one. If you do that, you will get this equation, right? So you will find this is the so it is negative, indicating that the voltage will come down. Okay, so VDD minus VTN Cx divided by Cy. So this was the issue with dynamic logic. Here I had made some mistake in the last slide in the last class. So here, if you see here, now we are assuming that Cx is very large, right? So some, as the charge is getting shared from here to here, it cannot reach the maximum value, because that much charge is not available at Cx, because Cx is available initially with Cy, because Cx is now large. So what happens is it will keep getting charged till these two voltages become equal. After that, it cannot go beyond that, so it has not reached the maximum value. So in that case, if you write an equation, this is the initial voltage which is available across Cy. This is the voltage after charge sharing. This is the voltage across Cx. Now Vx and Vy, they are the same. Okay, in this case, so we substitute that by Vy here, and then we write the we just get an Vy minus VDD. If you do that, we get as minus VDD Cx divided by Cx plus Cy. So these are the two issues in which the dynamic circuit suffers from. Is this clear to all of you? Yeah. Okay. Now there is one more issue. We cannot cascade dynamic gates. Okay, there is an issue in cascading dynamic gates. Cascading means one dynamic gate driving another dynamic gate. Okay, for simplicity, it is just shown one inverter driving other inverter. It need not be an inverter, but it could be a complex and a dynamic gate also. Okay, why this is no, these are equal is, suppose initially there is some now this is VDD, now some charge is coming here, so this voltage will keep coming up. So it is so there is no adequate charge available for it to go to VDD minus VTN. Okay, that is the maximum which is, but it is still it is lesser than VDD minus VTN, but these two voltages become equal. After that they can't and no current can flow, right? So that is the condition which we have taken. Is it okay, Bera? Yeah, in the first case it's, yeah, in the if I go back to the first case, here this Cx is small. Okay, so a small charge, if Cx is small, what is the equation of Cx? Okay, it is Q by V, right? So if Cx is small, if I take it will be Q divided by V. For a small charge, large VDD variation is possible. So this can go up to VDD minus VTN in case Cx is much smaller than Vx. Okay, between Vx will be no, it will get charged to VDD minus VTN. And then it will stop there, because this is an NMOS, so you can't have an voltage beyond VDD minus VTN. Okay, okay. So here we said there is an issue with cascading. We are ignoring VDS of A. In this case, no, this will be in an on state, so there won't be any VDS across here, right? Okay, so it will be in an on state, so there won't be any VDS. Okay, so there is an issue with cascading of dynamic gates. Okay, now suppose now you say the input is 1 out here. Okay, and then when the input is 1 here, the clock is going high, so this is getting pre-charged to 1. Okay, and then when the clock is no, when the clock is low, this node has got pre-charged to 1. So output is pre-charged to 1. This output is also pre-charged to 1, right? And both of them are pre-charged to 1. Now suppose the clock is going high, so this gate is enabled, this gate is enabled. So since it is 1 here, this has to come to 0 and this has go to 1, right? That should be the final case. Okay, these are two inverters, right? During the pre-charge period, both are during the pre-charge. This is the pre-charge period. Both of them have been charged to high, right? During the evaluation phase, when the clock is going high, what should be the ideal condition? Since it is 1, it should be 0 here, and this should be 1 here, right? In the ideal case. But what happens is, this is 1, right? Initially during pre-charge, it will take some time for this to get discharged. So there will be some propagation delay. So during that propagation delay, since it is 1 here, this charge also 1 also starts falling down, right? And see, if you see here, now this is coming, this is taking time, output 1, okay, for it to die down, okay, after the clock is going high. So till it reaches VTN, since this voltage reaches VTN, cutoff of this transistor, the output also starts falling. So you will have the full voltage of VDD not available at this output. And when the clock is high in the evaluation phase, there is no way this can be charged back again to VDD. So you see these gates have an issue of cascading. Is this aspect clear to all of you? Yeah, is it okay? See, if you are having difficulty, let me know. Okay, so because this is charged to 1, this is also charged to 1 during pre-charge. During evaluation, this is 1, so this will go to 0, and this is supposed to remain 1, right? But till there is a propagation delay for this node to come to 0. So till the time this output reaches a VTN, okay, this transistor remains on, and hence you will find a VDD coming low, and there is no way to build this up back to VDD unless you keep an keeper transistor. So once you cascade out here, so there could be an issue. So this is one more issue with the dynamic logic. So to overcome these problems, we have something known as the domino logic. Okay, in the domino logic, okay, there are two things which has been done. From here, from the output, you have kept an weak PMOS. This we saw last time also. This is known as an keeper transistor. Okay, but the thing is, you have to keep it weak. So you might have to not only keep the width minimum, you might have to increase the length of the transistor also, so that to keep it in a fairly weak. Otherwise, there will be an during switching, there will be from VDD to ground, there could be an connection available, right? So this has to this has to overcome this PMOS and pull this thing to down this node during evaluation phase, right? So see. So for that, because when it is pre-charged, it will be 1, right? It will be 0 here. So this will be on. During evaluation, this transistor will go, but this will continue to remain on. But this has to be strong enough to pull it to 0. If it is 0, then this 1 is available here. This 0 will be available here. So this will keep it at full VDD. So the problem of charge sharing is not there. But however, we have to be careful that if it is an if this has to be weak. Otherwise, what happens is during evaluation phase, this will not be able to pull this output node to 0. Okay, cursor is not visible. I'm actually using an pen, that is the reason. Okay, so that is an problem with the domino logic. Okay, so that is the reason we have to keep this as weak. Now if I keep this weak, okay, now the problem, so this have to keep I have to keep it in a weak. That is one safety measure you need to take. And then in the domino logic, I have one more inverter, which is no. Okay, so I have one more inverter which has been inserted here, right? So this is what the domino logic is. Now what is the advantage of having this inverter? We'll see that. Okay, now if you see here, if I have an inverter out here, now the cascading is not a problem, right? So one inverter I have placed it here, which will resolve my charge sharing problem, and this inverter which is placed here will not cause any cascading issues. Okay, so how is it not making an issue with the cascading is, now this node A will be pre-charged to 1, right, during when the clock is low. Node C will be pre-charged to 0. Okay, this is going to be pre-charged to 0, right? It is not going to be pre-charged to 1. Now suppose this is 1 out here, right? So it will take for it this time to become 0, right? And then slowly so by the time it goes to 0, then this will slowly go up, right? So there will be a propagation delay. Now the propagation delay will be from 0 to 1 out here, right? But a 1 out here will not cause this node to get discharged out here. So you can easily cascade these two gates without having any issues. Is this okay? Let me explain that to you, right? So during pre-charge, this is pre-charge to 1, this is pre-charge to 0, right? This is pre-charge to 1, this will be pre-charge to 0. During evaluation phase, this will slowly come down to 0. Now since it is 0 out here, this will continue to remain 1. So this discharging, okay, even if it is going to take time, doesn't affect this 1 out here, right? So after some time this 0 is this is 0, this is going to go to 1 out here, right? And then when it is becoming 1, then it will get discharged out here. So there is no issue out here like the contention. So that the problem which we saw in the this particular problem is not seen out in these kind of circuits where you have one inverter out here. Is it okay? Yeah, Vishnu, is it okay? So what is happening here, right? Okay. So if you see here, so since it is a 0 is there here, okay, let me repeat it. Okay, in the dynamic logic, what is happening is this aspect clear? In the dynamic logic, you have 1 out here, right? So this is being discharged to 0, right? This is two inverters which are cascaded. So I have an if I have a 1 here, it should be 0 here and it should be 1 here. But what happens, this is 1 here, pre-charge to 1 here, this is taking some propagation delay now for this to get discharged. During that time, this output node is also getting discharged. So this is the issue with the dynamic logic. In the domino logic, what is happened, I have put one more inverter here. So this is 1 here, so this is 1 here. So this is an positive logic. Okay, it is not an inverter. This entire thing is not an inverter. Okay, in the domino logic, you have positive logics. Okay, 1 is here, so 1 will be available here, right? So you can make an AND gate, you can make an OR gate. You cannot make a NAND gate in a domino logic. You can only make positive logics. So this is 1 here, so this is also a 1 here. So now initially during pre-charge, but however during pre-charge, this will be pre-charged to 1, so this will be pre-charged to 0 here, and subsequently during evaluation case, this will rise to 1, right? Since initially it is 0 out here, so this gate is actually, this pre-charged 1 value will be still be there. It will not get affected because it is 0 out here. Subsequently, when it becomes 1, okay, then this will get discharged to 0. And if it is continues to, if, suppose instead of 1 it is 0 here, then also there is no problem. Okay, then this will continue to remain 1, this will continue to remain 0, and this will continue to remain 1. So in either if it is 1 or it is 0, so there won't be any issue. In both the cases, this will work fine. Is it okay now? Yeah, okay. So this is how in one of my simulations, in one of my papers with TFETs, I had implemented domino logic. So this was an carry, and this was the sum module. This is a full adder. So if you see here, this is the pull down network for the carry, right? And then you have this gives carry bar, right? So then I can generate carry, and I can use that carry signal as an for the keeper transistor. So that has been done here, right? And then you again use the carry bar here, and this is the pull down network for the sum, and you use an inverter to generate the sum, and that has been used to drive the weak PMOS. So this is how a domino logic looks like. So here this is what we discussed out here. So here if you see here, this is getting pre-charged to 1, right? So this point, this will be pre-charged to 0 out here, right? Now from here it can either remain from 1 to 1, or it can go from 1 to 0 out here, right? So here at this node it can remain on a 0, or it can go from 0 to 1. So since you are not having a transition, the problem comes when does the problem come? If there is a transition from 1 to 0, right? If there is a transition from 1 to 0, if there is an during 1, it will start discharging. So that issue is not available in the dynamic logic. Okay. So in the domino logic, so why is it known as a domino logic? Okay, so that is explained here. A domino is generally like if you have a set of cords and placed vertically, and if you push one, it will keep falling. So that is known as the domino effect, right? So similarly here also, since if you see a chain of inverters is here, right? Now if you see here, when this goes 1, right, and this node goes to 0, then this becomes 1 here, and that will pull down this node to 0, then this will become 1 here, that will pull down it to 0. So the moment evaluation signal comes, if you have a chain of inverters like this, okay, the nodes will get it will propagate like this, 0 1 0 0 1. Is it understood? Suppose it is all pre-charged to all the these are pre-charged to 1, and these are pre-charged to 1, 0 1, okay, 0, this will be pre-charged to 1, this will be pre-charged to 0, right, this is 1 and pre-charged to 0. The moment this is during the evaluation force, if it is 1 here, this will become 0 here, this will become 1, this will become 0 1, so it will just go like this, right? So that is why it is known as this logic is known as domino logic. Okay. Now there is an issue with the before discussing the drawbacks, okay, let's discuss one more issue. So if you see here, okay, this transistor, is it really required? Okay, so if you see, this is one dynamic logic. In the first stages, we require this transistor, and we require this transistor also. This is to pre-charge it, and during pre-charge, you don't want the PDN network, right? You don't want the PDN network during pre-charge. During pre-charge time, this will ensure that this PDN network is not pulling this voltage to 0. So this is essential in the first stage. But suppose I have from second stage onwards, where I have all the inputs coming here from the various other dynamic domino logic circuits, okay, from the other domino logic circuits. So what will be the voltage available here? It will be 0 here during pre-charge. What will be the voltage available here? This is also coming from one more domino logic, right? So it will also be 0 out here, right? So that means this PDN network will as such be disabled. So is there a requirement of this? There is no requirement, right? So you may do away with this transistor. You can have only this transistor, right, the tail transistor, this known as the tail transistor, okay, can only in the first stages, but you can probably we'll see there is an issue with eliminating it, but otherwise we can eliminate this transistor here from the second stage onwards, because during the pre-charge period, all the inputs coming from other domino logics will be 0. So the PDM network, so there is no, the purpose of this is to disable the PDN network during pre-charge period. So that is as such disabled, because all the inputs will be 0 here, right? So during the evaluation phase, then these signals can become 1. So this will be off. So based on that, and this node will either remain at 1 or it will get discharged to 0. Why are we not putting keeper in the first stage out here, right? Yeah, you can keep a keeper here also. In this particular circuit, we are just discussing. You can have it at each node keeper circuits, not an issue. We can keep a keeper here also, right? Okay. Here, this can be eliminated, right? So now we'll see that. So this particular, and if you eliminate it, it will be known as an footless domino. Okay, the foot has been eliminated here. So if you see here, it is only pre-charging the nodes out here, and the inputs are just pulling it down. Okay, so but there is an issue here. Now if you see, the pre-charge is rippling, and it is there will be a short circuit current. So let's see what is this issue. Now suppose initially this is 1 out here during this is 1. It is an 1 out here, right? Suppose during the evaluation phase, and during the evaluation phase, and this is 1 out here, right? So the moment clock goes low, this will be switched on, and then there will be a short circuit current like here. Okay, because for this during evaluation, during the pre-charge period, okay, this transistor will be pre-charged to 1, and it will take some time for this to get to 0 here, right, from here. So during that period, you will find there is a short circuit out here. Is it understood? Let me explain this once again, right? Suppose during the evaluation phase, okay, I am talking about the evaluation phase. Initially it is 1 out here. Okay, now the clock is going from high to low, right? So this has got switched on, right? Now we are telling this there. Now if you see, there is a short circuit path from here to here. Okay, initially we removed that transistor, assuming that during the evaluation phase this will be 0 as such, we said, right? But there will be this 0, no, because it was in the evaluation phase it was 1. It will take some time for this signal to go to 0. There will be a propagation delay. Okay, because if you see, this has to be pre-charged to 1 out here, and then from the inverter it has to come to 0 here. So during that time there will be an short circuit current here. So that this will not only happen here, it will happen in the other subsequent stages also. So that is why footless domino, although you save one transistor, but you might land up at increased short circuit currents. So this is not used. So generally we keep the foot transistor also. Is it okay with all of you? Yeah, okay. So now the problem with the domino logic is, so there is a limitation in the domino logic also. It says we cannot implement inverting switching functions. Okay, there should be no. Here we are saying that yeah, in the first stage as such there has to be enable, but we are saying if it is most for power efficient circuits, we should have enable in all the stages. Otherwise there will be an short circuit issue. Okay, so there will be an although we can remove it, okay, but to prevent short circuit, to be more power efficient, we need to keep the, so footless domino is generally not used. Okay, so we keep this transistor. Okay, so that is the issue. So this has been told in the textbook, but then if you do little bit more research on footless domino, you will find there is an issue like this. Okay, so this is available in some of the research papers where it will tell that there is an issue with the footless domino. So these kind of short circuits will be there. Okay. So now there is a problem with the domino circuit, that inverting functions cannot be made directly. Like you can have an AND gate, because there is one more inverter which is placed out here, right, in the domino logic. So you can't make an NAND gate. Okay, so you can't make an NOT gate, right? You can't make an XOR gate. So this is an issue here, right? So that becomes an a problem for domino logic. So this is one way of implementing an non-inverting function, or you can implement a non-inverting function like this also. You invert the inputs and you implement an F bar here and F out here, right? So these are the two kinds of two methods of implementing a non-inverting function out here, right? So this property can be used to simplify some of the domino logics. Like there is an inverter here and there is an inverter here. So right, this is a non-inverting function, this is also a non-inverting function. So these two inverters and they get cancelled out here. Okay, this will be clear in the next slide what I want to say. Okay, similarly in this case, okay, this is an in and this is out, so this becomes in bar and out bar. Okay, so you can cascade two non-inverting functions, inverting functions out here, and remove these two inverters. Okay, what I am coming to will be clear in the next slide. Suppose you have you need to implement a dynamic logic. So this is an OR gate. Okay, I think this has been made NAND out here. So this is an OR gate. Okay, you have an A, and then you have F2, another OR out here, and here OR out here. So if you see here, this F1 has been implemented as an OR gate, dynamic OR gate. Okay, you are supposed to have an inverter out here, right? So here you have implemented F2 also, okay, with an OR gate. Like you have taken A as one of the inputs. There are other inputs also available here, okay, but then you have not put an inverter here. So here I am going to get as an this function out here, because these two inverters, because this is also these two inverters have got cancelled out here, right? So both are non-inverting functions here, right? So you have both these two inverters. Now what is available out here, okay, from here and from here, they get cancelled here. In the next stage also, again, if I see here, okay, this is an AND gate out here. So I can have one AND gate out here, right? And then I have this is another AND gate. So I have another AND gate out here. B is given here, and these two inverters are also have been removed out here, and F4 is an OR gate. So you can do such kind of things. It will remain like a domino logic, but all those inverters there which gets cancelled out each other. Okay, so this is the way we can design a domino logic, where we can like the two inverters which are available, so they can be they get cancelled each other if you design it properly. Okay, so this is how we go about designing an domino logic, right? So other way of overcoming the issue of non-inverting functions not available being in a domino logic is by using dual rail domino. Okay, what is dual rail? Say you pre-charge, this is a pull down network, so you have two pull down networks, right? So one is one pull down network is with F, the other one is with F bar. So if you pre-charge both these nodes out here initially, so this will be 0 out here during pre-charge, this will also be 0 here, so this will be 1 and this will be 1 here, right? So in that case it is invalid, because it is an pre-charged phase, right? Okay, that is pre-charged phase. You cannot have no, so sorry, this will be pre-charged to 1. Both these nodes will be pre-charged to 1, so it will be 0 here and it will be 0 out here, right? So this is 0 0, that means it is pre-charged. Okay, and during the evaluation these two transistors will be switched on, and this transistor will be switched on during evaluation. So one of them, F or F bar, will pull this node to 0. So either it will be 0 1 or 1 0 here, okay, depending on the function. So in this case it will have 0 and 1 out here, the final output. 1 1 is an invalid output, so you can't have 1 1 in any case out here. So that means there is some issue. Okay, this can happen only during while it is being while this is soon after the no, this can never happen, right? 1 1 both can never go that. Okay, so this is an invalid state. So this can be, and this is pre-charged. 0 0 means it is just it is a pre-charge. Otherwise the outputs have to be complemented to each other. Okay, so if now Y and Y bar is available, so it becomes easy for, because when you make a K map or anything, you might require, you have generated one set of functions, then again you are using that functions in another K map, so you might require F and F bar also there also, right? Y and Y bar also there, right? And domino logic, if it doesn't give Y bar, then it becomes a problem. So you can use this in a dual rail kind of thing to generate both Y and Y bar, which can be used in the next stage. Is it okay with all of you? Yeah. So this is again implementation of the dual rail. Like if you have A B out here, right? And here it is they are in AND configuration here, they are in the OR configuration here. So this will give an AB out here, and it will give A bar B bar here, right? So this is like this is NAND, right? So now here you have an this in the OR configuration, so you will find it, you will get it as AB out here. So this is known as the dual rail domino logic. This is how we do this. Okay, so okay, you can also have a multiple output domino. Like if you see here during pre-charge period, okay, this node is charged to 1. Also this node is also charged to 1, because you have one more transistor here, and then you have a clock here. This also will be pre-charged to 1 out here, right? And then you can take an output from here. So this will be C plus D, right? Then C or D, because you have an C and D here. And similarly from this node it will be B and C or D here, right? Now if you see here, they are all non-inverting output which is available, okay, in domino, because there is an inverter here, it will always be non-inverting. So C plus D you get, B into B and C or D you will get it from here, and from here you get an A and B and then the C or D function. So you can get from a single structure, from multiple nodes, you can take multiple outputs. So this way you can probably optimize your circuits where you require multiple outputs. Okay, so this also can be done in a domino circuit, right? This is something known as compound domino. Here if you see, this is the function, right? Now if you try to implement this function, you will find this will require a huge stack of transistors, like around 5 of them on one on top of that, and then you will have one evaluation transistor and one pre-charge transistors also. So that will make it a total height of the circuit to be 7 transistors, right? No, 6. It will make it as 8. So in those cases you can split the circuit, okay? Like if you can write this as it into 2 out here, right? And then you can do this algebraic manipulation. So you have ABC bar plus ABC bar, the whole bar, right? So when you by De Morgan's theorem, when it comes, it will become the same thing, right? And then again you are putting a bar out here and a bar out here, and this OR now becomes an AND, because you have put an this bar outside here, and then you have put one more inverting options out here. So this particular expression can now be implemented like this, right? So you have ABC, this will generate ABC bar, this will generate an DEF bar, and then you are giving it to an OR gate, and then you have GH bar here, and then you are giving it to an NAND gate. So this is how a compound, if you have a very big function, you can use these kind of circuits to make it so that the stack is replaced by the stacks, big stacks are replaced by small parallel structures. So this is known as compound domino logic, right? Okay, so the last kind of logic, which, but this is actually this is this is dynamic logic. Essentially this is a dynamic logic. It is known as compound domino logic because you are I'm not sure, because it is dynamic logic in fact. Maybe because this is in implementing a positive logic, okay. So essentially finally you are using an OR gate out here, and one more, instead of an inverter you have a NAND gate out here, right? So it is coming out as an right, it is coming out as an finally as an positive output, right? So that is why, that is the reason it is known as compound domino logic. Okay. Now you can also have an np-CMOS logic. Okay, here what you see here is this, here you are implementing one function with pull down network, and here this is an pull up network. Okay, and during the pre-charge period, this is pre-charged to VDD, right? During pre-charge period, this is pre-charged to VDD, while you are giving clock bar out here, right? So this is giving clock bar out here, okay, here instead of clock. So what will happen is here during the pre-charge period, since this will be 1 out here, so this will be pre-charged to 0. This node will be pre-charged to 0, right? This will be pre-charged to 1 out here. So you don't have that issue of cascading out here. What happens is, what happens to this node? Either it remains 1 or it can go to 0, right? These are the two conditions which can happen. Suppose this is 1. What happens, right? This is a pull up network, right? So this continues to remain off out here, because a 1 will keep the PMOS off. So this will continue to remain 0. So there is no issue. Suppose it is going from 1 to 0. If it is going 1 to 0, in that case this will be switched on, and then this will go from 0 to 1 here. So there is no issues out here, right? The issues of cascading, which we saw here in the dynamic logic, okay, we have this is issues like here we had an issue, this going from 1 to 0, okay, causing a drop in voltage here. So that is not happening out here. Yeah, it is something like a master slave flip-flop, you can call that, right? So because this is pre-charged to 1, this node is pre-charged to 1, but here I am using on a pull up network, and for a pull up network, when it is going from 1 to 0, right, if it is 1, this remains switched off. So there is so this will continue to remain 0, and as and when this output goes to 0 with certain propagation delay, doesn't matter. So this will also go from 0 to 1, because when it goes to 0, this will be switched on and this node will get charged to 1. So there is no issue with what cascading of these kind of nodes. So if you have one pull down network, then one pull up network, then again a pull down network, so you can build up a dynamic logic in a chain like this, without having to bother about the issues of cascading. Okay, so this is one family which is actually used in many circuits these days. Okay, so the only problem out here in this particular circuit is, since you are using a pull up network, here to keep the propagation delays, you will have to use large PMOS devices, right? So that for that, so there is an issue with the large capacitance will like to, if you have to keep the propagation delays, then extra area and extra power, okay, so they will contribute towards extra capacitance. So that is one of the drawbacks which you have with the np-CMOS issue. Okay, so we'll take a 10 minutes break here. It is 11:16, 11:26 we will assemble back. Okay, thanks a lot.